Let's begin. Little thought experiment. Let's suppose I take a baseball. We have a baseball playing game, and I throw a baseball to you. No, I don't throw it to you. I have a little machine that throws a baseball. You ever see those things? And it throws a machine. And that machine can only throw the baseball at 30 meters per second. That's how fast. 30 meters per second. It's all regulated to throw that fast. Now, it's going to throw the ball to you. You got your catcher's mitt. Hit, boom, you catch. How fast do you catch it? 30 meters per second, right? That's because the machine is at relative rest to you. There's no motion between you and the machine. So you're going to catch it at 30 meters per second. Now, let's suppose you're in a truck, and the truck is going that way at 10 meters per second. 10. Get that? I throw the ball just like before. You catch it. How fast is it going? We'll check your neighbor. You're going away. You're moving away from it. Faster or slower, gang? Slower. In fact, what's the answer? 20. You're going to catch it at 20 meters per second, right? About-ish. Let's suppose you turn that truck around and you come toward the ball-throwing machine. And the ball-throwing machine throws just like before, 30. But you're now moving this way at 10 meters per second. When you catch the ball, that ball is going to hit your glove at what speed? 40. We can do that, right? And if you got outside and you did that, and you found out that when you traveled away, it hits slower, and when you travel to it, it hits faster, you would not be surprised. You would expect that. And there might be some quibbling. Does it really come out to be exactly 30, exactly 40? But the speedometer might be off. How about if we did this, really, and no matter how you moved, every time you caught the ball, you still caught it at 30 meters per second. Whether you're racing toward the machine, still, or racing away from the machine, and you know that machine can only throw at 30, and every time you catch it at the 30, how about it? Would that be a little W-I-L-D? Huh? Yeah. Well, that would really be what. That kind of shake you up a little bit. You'd start to say, wait a minute, am I dreaming something wrong here, right? Well, let me tell you, a similar thing happened, gang. A similar thing happened just before the turn of the century, 1800s. It turned out they found out that light has the same speed for all observers. Whether the light source is coming to you, away, or whether you're moving away, make no difference. Every time the speed of light was measured, has the same value, 300,000 kilometers per second. And every measurement showed it to be the same. When the Earth is racing toward a star, toward the sun, or toward a star or something, the same speed as 6 months later when it's racing away. Same speed all the time. This had a lot of people upset. The physics community was starting to shake a little bit. And about this time, there was a fellow who was going through school. At the age of 4, he could hardly talk. In grade school, didn't really stand out too much, but he plugged away. And an uncle gave this fellow a compass on his 9th birthday or something like that. He said, how come the compass always points north? And the uncle says, well, it always points north. The young fellow says, well, HC. And the uncle says, I don't be knowing such thing. I mean, there's probably no reason for that. Compasses just point north, okay? I'm making this up a little bit, yeah? But it turns out, who are we talking about now? Albert Einstein. And Albert Einstein went through school. Oh, he took algebra in high school and flunked. Hey, don't knock it. Some people pass, some people flunk. I mean, just one of the ones that flunked, okay? Don't make a big deal of it. And some people get a high school diploma and some people don't, right? Some can hack it, some can't, right? Well, Einstein couldn't hack it. That's all right. You know, you can still make it. No high school diploma, gang. And he's out there, and it turned out he met a young lady who influenced him to go back to school. So he tried going back to school. Already took the entrance exams and flunked. And he flunked the exam. Hey, I mean, not everybody passed everything, yeah? And then he studied hard, and he took the entrance exams again and passed. Turned out he had trouble with the French language. You know, in Europe, they speak all these languages. He couldn't do the French so well. Anyway, Albert Einstein went through school, and he did go all the way and got his FUD in physics. And about this time, he had a hard time getting a job. His thinking was a little bit, well, for one thing, he didn't have a high regard for many of the ideas at the time. You know, we always name the streets after military heroes, you know, and if someone really, man, butchers millions of people, man, they put a big monument in the thing for him. Right? Einstein thought that was kind of upside down, that we weren't choosing our heroes very properly. You know, he had kind of funny idea. Anyway, it wasn't too popular and had some trouble getting a job. But he did get a job with the help of his lady friend again. And he got on the at the patent office, I guess, in Switzerland, going over patents that were being submitted. And here's the guy with his FUD in physics and all that. Anyway, he was interested also in light. He asked a teacher one time, what would a light beam look like as it goes by? Teacher, it's going too fast, you can't see it. He said, well, what if you go along with it and take a look? What do you mean, what if you go along with it and take a look? Well, how would it look? Would it be a little squiggly way? What would it look like? And he's all the time asking questions like that, never getting any answers. And he was wondering about the bit with light having the same speed for all observers. It's a matter of some history whether he knew about the experiments by Michelson and Morley, read about that told that the light speed was the same for all observers. It's even questionable as to whether he knew about that experiment. But the more he thought about light, the more he realized that if you did travel with light, it would look just as if you were at rest. And everyone ought to see the speed of light traveling the same, regardless of their motion. And here's some of the reasoning that kind of went into that. Let's look at what speed is by definition. What is speed? See, the speed of light's the same for everyone that measures it. What's speed? It's distance compared to time. Distance through what? Space, okay? So it's really space compared to time, see? We measure it kilometers per hour, okay? Meters per second, okay? Space per time. And Einstein realized that the reason the speed of light is constant, if in some instance perhaps maybe more space should be travel through, then corresponding to that, more time will be taken. And if something happens where maybe it puts only a small bit of space because of motion, then the time will be smaller in turn. Einstein realized that the ratio of space to time for light would be constant, like the ratio of the circumference of a circle to the diameter. For a big circle, a little circle, boom, that ratio is a constant. And Einstein felt that these two were related. Who would think that what time it is on your clock would be related to like space as we know it? Space and time. Einstein said that if you travel through space, you'll also travel through time. How? Such that the ratio of space to time for light will be constant. So we do know the speed of light is a constant. And that's one of the postulates of Einstein's special theory of relativity. Everyone who measures the speed of light will get the same value. Now, that has some interesting consequences. Let's try a little thought experiment here. I'm going to throw this piece of chalk up in the air. Now, we're all observing what's happening here. Let's suppose we made measurements as to the speed of the chalk. In this case, it varies, because it's going quickly here, slow, 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 and it's accelerating, okay? So we'll just kind of fudge it off a little bit. Let's talk about the average speed. We would get the average speed by taking the distance divided by the time. That would give us the average speed. And let's suppose every one of us makes careful measurements, and we all get the same average speed, okay? But here's the postulate, that no matter how I move, we will still all get the same average speed. Well, right here, this is not controversial. You see it go up, you see it go down. You see it go through that particular space, and you measure on your watches that particular time. I measure the same thing. I measure the same space. I measure the same time. We all get the same value. I'm going to repeat. This time I'm going to move. I'm going to look at it, and you look at it. I see the same thing as before. I saw the same thing as before. Okay? I saw it go straight up and straight down. Get in an airplane and flip a coin. What's the path? Straight up and down, right? Now get outside the airplane and look at the path. Okay? You guys saw this. Watch again. You guys saw it go like this. Now, if you get the same speed, you don't. You really saw it moving faster. But if you got the same speed, if the speed is the same, and the space is admittedly bigger, then the only way you can get the same speed, gang, is if you get a longer what? Begin with a T. Time. And so your witnessing of that event, your timing of the event, and my timing of the event would be different. A lot or a little? Begins with an L. No. A little bit different, okay? but I exaggerate the figures. The ratios, the same. Einstein could see that something's funny going on with light, too. Because take this example. Einstein at one time is sitting in a cable car. Going to take the cable car through the streets. And looks up and sees the village clock. In every village, I always have a big tower and a big clock on there, okay? And the clock says, going to work in the morning. And the clock says 8 o'clock. Okay, that means the little hand's on the 8 and the big hand's on the 12. You hear me? Okay? Now, Einstein's sitting there and he says, what does it mean to say the clock reads 8 o'clock? What it means is that light is bouncing off the clock and coming down and giving the information 8 o'clock. If it's midnight and there's no lights around and the moon's out, he's not going to see anything. But it's in the daytime in the morning, yeah? So he sees 8 o'clock. Einstein wonders, wow, 8 o'clock, boom, hit me like that. What happened? I moved my head. Won't the 8 o'clock keep going? Now the 8 o'clock is, maybe some guy way, way down there later on, boom, says it's 8 o'clock. No, it's 8 o'clock when it passed me. But how about some guy way, way down there? How about some guy on some planet way, way out there? It takes time for that 8 o'clock information to move. Isn't that true? Yeah? When light leaves the sun, you know how long it takes to get to us? 8 minutes. The sun is 8 light minutes away, gang. 8 minutes away, see? Okay. So anyway, Einstein wonders, that 8 o'clock information keeps going. Now, what if this cable car started traveling along with it? And what if this cable car went as fast as light goes? And the cable car keeps going out. Occupants in the cable car would look at the clock and they'd see what, gang? How would they see the clock? What would the clock say? 8, 8, 8, 8, 8, 8, 8. He would see time frozen. At least the clock. Is that understandable? See? So he'd see the time completely frozen. So Einstein realized if he stays still, he can watch that clock do its thing at the rate that we call 24 hours per day. 12 hours it comes all the way around one time, yeah? But Einstein realized if he moves as fast as light, then he sees it frozen. Now, oftentimes when you're thinking about ideas, it's nice to look at the extremes. He's looking at the extremes there. One extreme is 0 speed, what do we say? The ultimate speed, what do we say? And they're quite different. Now, what's in between? What's in between 0 and the speed of light? Do we see the clock slowing down? Do we see the clock running a little slower? How about it, gang? Check your neighbor. If you went like near the speed of light, but not quite the speed of light, would you see the clock running just as fast as if you stayed still? Think about that and discuss it. Hey. How about it, gang? How many say, yeah, I think it would go slower? I think we would see it going slower anyway. From our frame of reference, we would see the time slower. Yay. That's right. I want to talk to you about the twin trip, which is discussed in the book, but I want to preface something. I want to preface that trip with a little hardcore physics. Pay attention, gang. Let's suppose someone's standing on a planet here, and they have a flashlight, and they shine a flashlight off to a distant planet over here. And people on this distant planet are going to have a telescope all lined up here, and they can kind of stand right here, and they can watch the flashes of light. And let's suppose a person here emits a flash of light every 3 minutes. This little flash, flash. I got a question for you. If there's no relative motion between the two planets, it's going to take some time for that first flash to get up here. But an observer up here, boom, sees a flash. How long are they going to have to wait for another one? 3. And the next one? 3. And the next one? 3. They'll come at regularly spaced intervals, all right? Now let's suppose I have a rocket ship that's traveling at a very, very high speed between the two planets. Now this rocket ship is traveling away from the planet, the source of light. Will that rocket ship see the flashes as often as 3 minutes apart? Or more compressed to more often than 3 minutes apart? Or kind of stretched out? Check your neighbor. See, the rocket ship catches this flash. If the rocket ship waits here, this flash will come by in 3 minutes. But the rocket ship doesn't wait there. The rocket ship travels up here. So that 3-minute flash is going to be stretched out a little bit. Do you see that? So the flashes will be seen less frequently. Same speed, but less frequently. Difference now, okay? Let's pretend that the rocket ship travels so fast that the rocket ship sees the flashes 6 minutes apart. Can we see that that could be the case? Okay? So the rocket ship sees them 6 minutes apart. It's like when you're listening to sound. Now you travel away from it kind of goes down, right? The pitch goes down. Here's sort of the pitch is going down. The frequency at which you see those flashes goes down if you move away. This is called the Doppler effect. Okay? So this person sees them every 6 minutes. Now we're going to invoke Einstein's first postulate, that all light is seen to travel at the same speed by all observers. What the ship does is every time it receives a flash, it's got its own little beacon here, and it emits a flash. And it directs those flashes to this observer. Now, these flashes are going to be emitted every 6 minutes on the rocket ship. But won't the flashes keep right up with the flashes by the Earth types? So let me ask you a question. These 6-minute flashes, 6 minutes apart flashes, are going to be seen by this observer to be how many minutes apart? 3. So when the Rocketeer gets up here, he's going to say to his friend, hey, how'd you like my flashes 6 minutes apart? The friend's going to say, with all due respect, those flashes, honey, were 3 minutes apart. You know, they were 6. He says, I saw them at 3. Could be? Yes. So 6-minute flashes by a moving source can be seen over here to be 3 minutes apart. Let's put that information over here. A person seeing that ship approach will see 6-minute flashes 6 minutes apart every 3 minutes. Okay? Now, let's come back here and look. Every 3 minutes, they're blipped off. Sees them at 6. I'm going to ask you a question to use your reasoning. Let's suppose instead the observer, the sender over here, sent them every 6 minutes. You know, half as many flashes. If they were sent every 6 and nothing changed, how often would they be seen here? Every 12. Now, here's Einstein's second postulate. All the laws of physics will be seen to be the same in uniformly moving reference frames. This is moving uniformly with respect to this. In fact, Einstein said it makes no difference whether this is at rest and this is moving, or this is at rest and this is moving away. Motion really is relative. There's a relative motion between the planet and the ship. So let me ask you a question. These 6-minute flashes that the ship really is sending the 6. We agreed on that before. These 6-minute flashes are going to be seen how long apart by that person back here who's now looking, who puts a telescope up and takes a look. Check your neighbor. What's the answer, gang? 12. Do you see that? I mean, if 6 is seen as 12, then 6 would be seen as 12. So we can complete this diagram up here and say this. We have another planet here. Person watching these ships, these flashes. Okay, what happens is really the flash is sort of like this. Okay, they're all scrunched up in here and all dragged out here, yeah? And so 6-minute will be seen 3 for approach, but for recession, 12 minutes. Do you kind of see that? Now, these flashes act as a clock. A clock is anything that's periodic. You could say the clock usually is a pendulum swinging back and forth, right? Or vibrations in a crystal lattice, okay? In this particular case, the clock is regularly spaced flashes of light. And one can keep track of time by counting up the flashes of light. So far, so good? Let's see what happens if we apply this to space travel. Here's the Earth, our cradle, gang. That's our cradle, the cradle of humankind. What do we do with cradles, by the way, even if they're comfortable? We outgrow them, that's right. And we see that starting to happen now, don't we? The spaceships going out, we're talking about space platforms, okay? Anyway, this is our cradle right here. And here comes our rocket ship, same one, streaming by. And we're going to say at this point, boom, both times are 12 noon. 12 o'clock on the ship, 12 o'clock on the Earth. And the ship continues. Now what the ship is going to do, it's going to take a 1-hour trip out, and it's going to turn around very quickly. so quickly that the time is negligible in comparison to the hour trip. So the ship is going to go out, whoop, and boom, turn around and come back. It's going to take 1 hour going out and 1 hour coming back with negligible turnaround time. And we're going to see how time compares for people on the ship who are moving relative to the Earth and how time compares on Earth relative to the ship. Now, 100 years ago, the answer would be SS. Same. But we find out nature is not that way. Nature is more interesting. Because watch what happens, gang. Our ship's going to go out for 60 minutes. On board the ship, we're going to emit a flash of light every 6 minutes. Okay? Every 6 minutes, we're going to emit a flash. And the people on the Earth are going to count the flashes. Then we're going to turn around and we're going to continue to emit a flash every 6 minutes. 6 minutes, precisely. Off goes a flash. Got it? Question time. During the outgo of the ship, that's 60 minutes, how many flashes will the ship get off? 10, 6 minutes apart, and you get 60 minutes. Try it. 10. 10 flashes. So while the ship is going away, it's going to emit 10 flashes. Those flashes will get to the Earth. The first one's right away. Okay. The flashes will ultimately get to the Earth. So the Earth type's going to set up a telescope, and they're going to start counting flashes. Okay. 10 flashes going away. Then it's going to turn around. When it comes back in, how many flashes are going to be emitted by the ship coming back in? 10. How many minutes apart? 6. Okay. So let's look at that. Ship point of view. Ship frame of reference. Going out. 10 flashes, 6 minutes apart, equal 60 minutes. Coming back in. 10 flashes, 6 minutes apart, equal 60 minutes. Total time, gang, 120 minutes. Convert that to hours. Can you do it? How many hours? 2 hours. Now, I got a question for you. When that ship, boom, as soon as it passes the Earth, what is the time on the ship? What's it going to be, gang? It's going to be at 2 o'clock, ain't it? It'll be 2 o'clock on the ship when the ship gets back. Do you believe that? Any funny business here? No. Straightforward stuff. 2 o'clock on the ship. They've been gone for 2 hours. Let's see what the Earth types think about that. The Earth types, how many flashes are they going to see for the ship going out? Begin with a T. 10. Okay. How often are these flashes going to be seen when the ship going away? 12. 12 minutes apiece, honey. 12. It's up here, huh? Going away, the 6 minute flash is going to be seen 12-minute intervals. Let's look. What's 12 times 10?
120 minutes.
120 minutes right there.
Shouldn't you label that the ship's point of view?
Oh, now I want to label this, yeah, Earth. Thank you very much. Saved again. Saved by Lee. All right, Lee. From the Earth frame of reference, 10 flashes would be seen 12 minutes, would be seen 120 minutes altogether. Gang! When the Earth type is looking at a telescope and sees that 10th flash, that's when the ship turns around. He's got the 10th flash. Then he looks down, or she looks down and looks at the watch. What does their watch say? 2 o'clock. The ship's still out there. Something going on. See why people got excited about relativity? Now the ship coming back in. How many flashes coming back in? How often are they going to be seen? 3. What's 10 threes?
30 minutes.
Even I can do that. Add those up.
150.
What's 150 in hours, gang?
2.5.
Can you see it's 2.5? 120 be 2, and then you got the, okay? So it's 2.5 hours. How much time has gone by on the Earth during this ship's 2-hour trip? 2.5 hours, gang. And when that ship comes back, what is the time on the Earth? On the ship, it's going to be 2. So it's taken a trip that long. But on the Earth, it's going to be 2:30. So what will seem to take 2 hours for the ship will take 2.5 hours for the Earth. So the traveling person doesn't age as much as the person who stays at home. Adventure gang, get out there and keep chugging. You notice I walk back and forth all the time, huh? All right? Yeah. Questions on that? Lee?
The point of view of the person in the ship, if we ignore the turnaround, which we gave negligible time, wouldn't it seem like the Earth went away at this speed and then came back at that same speed?
Yes. Yes, this is why it's been called the twin paradox. Why couldn't it as well be the same for the other observer? Why can't it be that maybe the spaceship is at rest and the Earth moves away? Okay. Well, here's the hitch. It's not a symmetrical situation, because that could, if that happened, the Earth moves away. Then the Earth, if it keeps moving away, we'll never know. But it's got to turn around and come back. And so one switches from one realm. I like to put it like this: switching space-time realms. You know, we all live in some particular space, don't we? It happens to be in this particular room right now, right? On the Earth, da-da-da-da-da-da, right? How about time? Do we all share the same time? Yes, we do. According to relativity theory, we're all at rest relative to one another. We will all agree with how fast clocks move. And we're all sharing the same realm of time. But as soon as I'm moving, now I'm in a different time than you guys are in. My clock is moving differently than yours. A lot or a little? Even without the hint, what is it? A little. That's right, because I'm moving how? A little. How about I move fast? How about I move like this fast? Then little turns into a lot. So it's a matter of degree. So when you move, you're in a different realm. You know you're traveling different space. Hey, you're in a different realm of time. And that is kind of wild. So what happens? It's the ship that's in one realm of time coming out and in another realm of time coming back. How about people on the Earth? One realm. And one way to check that is to bring a cup of coffee with you that's brim-filled. If the cup of coffee stays brim-filled, stays right there, then that's an indicator that you're not changing realms of time. But when you accelerate, the coffee spills. That acceleration marks the change from one realm of time to another. So they're in different realms. So it doesn't come back. They can meet again at the same space, but at the expense of time.
But when the rocket is going at a steady speed, wouldn't it see the Earth seem to be slowed down compared to it?
Yes, yes, yes. If flashes are being emitted by the Earth, then the ship sees those slowed down too. Would you like to see that? Can we get into that? How many people say, no, information overload, I've got too much to digest already? Can we switch frames of reference and see if it still works? Let's try it. Let's suppose instead of the fellow over here with the telescope, we put a person over here shining a light, okay? A light beam's going to go off, and now the ship observes, all right? Now, the person on Earth is going to flash a light every 6 minutes, okay? Now the ship's going out. Now the ship is going to watch those flashes. How long apart will those flashes appear to people on the ship? Do you see it's 12? Okay, they're going to go off for 60 of their minutes. How many flashes will they see 12 minutes apart in their 60 minutes? I don't know if you can figure that out. 5, good. So going out, the ship types are going to see 5 flashes.
Maybe we should put ship on for people.
Thank you, Lee. From the ship point of view, the ship's going out, it's going to see 5 flashes, 12 minutes apart. That's going to be 60 minutes, okay? Now, coming back in, the ship's going to see flashes how many minutes apart? Oh, you don't remember that? 3, okay? So the ship is going to see those flashes 3 minutes apart, okay? How many flashes is the ship going to get in its 1 hour? 3 minutes apart. You got to figure out how many 3s will go into 60. 20. So the ship is going to see 20 flashes coming back in, yeah? More flashes coming back in than going out. I mean, when the rain's coming down like this, you get fewer drops hitting you per minute this way. But when you turn around, and bam, 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 okay? Same type thing here. Now we get 20 flashes coming in 3 minutes apart. 23s is 60. Okay, so what time is it on the ship? 120 minutes, 2 hours. What time is it on the Earth? How many flashes have been emitted on the Earth during this trip? 25! So from the Earth. "25 sixes" of what, gang? E. Now let me ask you a question. You know when you see these guys, they get like they get the green pea and they get the 3 jars, and they go like this, like that, right? Which are ones that under, and you always guess wrong, but you know there's a catch because they're very, very skilled, and they're pulling something over on you, right? And you always, or a card trick, right? Right? Where's the catch? I've got a friend that does the card tricks, and I've even suspected, this guy is so good, I've even suspected him of really being magic and pretending he has skill. You know what I mean? He's so good, okay? But anyway, there's always a trick. Where's the trick here, gang? Where did I trick you into thinking that 2 hours on one frame of reference would be seen 2.5 hours on? Does that make sense? What did Einstein say common sense was? That layer of prejudice is laid down usually by the age of 18. This does not make sense to you. Because you know why? It's not part of your background. It's not part of your experience. This is off your experience. Maybe jet planes wouldn't make sense to a caveman. And this stuff is just starting to make sense to us, yeah? I'll tell you what, gang, there's no catch. As we understand it, nature is this way. Many, many experiments to see if there's something wrong about this. And all these experiments have only gone into confirming that Einstein was right. Let me say a neat thing about science, too. In a lot of fields, there'll be some sort of hero, like Einstein's our hero, yeah? We all love Einstein. Most of us do, yeah? So Einstein's our hero, and you tend to think, well, if it's a hero, you don't want to take shots at him. But in science, it's different. In science, a hero, schmiro. Everybody's trying to crack that hero and find something wrong. Everyone's attacking to see if they can find something wrong. And so science doesn't rest upon the reputation of some hero. Science rests upon everyone else trying to find a crack in that theory. And all attempts so far have only gone to substantiate this. Time really is different when you're moving. But I tell you what, we're going to talk more about these ideas next time. And you know what I want to do for you now? I want to share with you a film that a friend of mine made way back in 1976. When I was teaching these ideas in the early 70s, I discovered this kind of treatment at the class board. It's one thing about teaching, you learn at the class board. You know, you guys aren't the only ones learning. I learned too. And what I did at that time was to be able to see the ship at different positions. I made a whole lot of drawings, cartoons, and I took photographs and made slides. And I would get at the back of the room and I would show these slides in quick succession. I'd have a carousel, I'd hold the thing so I'd go click, 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 show the slides so you guys could see the ship at different positions. And about that time, my first edition of the book was out, and I went to a party over in Berkeley, and there was a fellow there who had just graduated from San Francisco State who was showing some of his movies. He was into movie making, cartoons. I really liked his cartoons. They had a warmth to them. I really liked them. Steve Smith. I say, Steve, you know, I've got this little thing I do with these little slides. I wonder maybe you could make up a little cartoon movie. We could make a movie of this and share it with more people. And at that time, he was working as a dishwasher down on Telegraph Avenue. And I said, Steve, quit the dishwashing. I'll grub stake you. I'll get your groceries, I'll feed you, and I'll grub stake you. Maybe City College will let you use some of their equipment, and we'll make a little animated movie. And he made an animated movie on everything that we just... Would you like to see it? Okay, roll it, Lionel. We see it right here, gang? And right here.
Where did the time go? Does anybody know? When did the day break? Did someone drop it? Was it a mistake? Did you know that time's different when you move at different speeds? That when you move through space, you change the rate at which you move into the future?
Well, you can't really notice these differences for everyday speeds, but for really high speeds, like for rockets traveling about half the speed of light, these time differences can be noticed. Let's take a look at the so-called twin paradox.
Well, bye. I don't know. I'll see you again.
Yeah, I guess maybe we're pretty interesting. Sure, you know, well, it's all in the
dark out there.
science. Well, it is dark.
We brought lunch, you know.
Now, while the traveling twin experiences weeks, the stay-at-home twin experiences years.
Something. No, I think I'll just sit here and do nothing. Yeah, that sounds like, yeah, I'll do that. Oh, what? What is going on out there? Oh, my goodness! I don't believe it. I didn't see you. I must relax. I can't relax. I'm too old to relax. Look at the style. Look at the size of this one. Yeah.
Could a situation like this be true? You bet it can. This is time dilation. We can see time dilation by comparing clocks from different frames of reference, say from the Earth and from a high-speed rocket ship. Now, a clock can be anything that measures periodic intervals of time. To simplify, we're going to let the ticks of our clock be periodic flashes of light. Look at the light flashes emitted by the stationary rocket ship. Now, some time goes by before they reach the distant planet, but since there's no relative motion involved, successive flashes get to the planet at regularly spaced intervals. That's to say, both the sender and the receiver will agree on the time intervals between the flashes. Now, there's nothing unusual about this. But suppose the rocket ship moves. Look at the Doppler effect. An observer sees the flashes at shorter intervals. Suppose the ship moves fast enough so an observer sees the flashes at intervals twice as short as the ship sends them. Then if the ship moves away, just as fast now, an observer is going to see intervals twice as long. Like if the rocket sends a flash every 6 minutes, they'll be seen every 12 minutes by the observer when the rocket moves away, but every 3 minutes when the rocket's approaching. Now let's apply this to time dilation. If the ship passes by the Earth and moves away at the same high speed for 1 hour, and quickly turns around and then returns in 1 hour, rocket ship time, this 2-hour trip is seen by the Earth as taking place not in 2 hours, but in 2.5 hours. And this is because the ship and the Earth have been in completely different realms of time. Let's look at this in greater detail. Suppose that when the ship goes by the Earth, that clocks on Earth and on the ship are synchronized to 12 noon. Then as the rocket leaves the Earth, a flash of light's emitted by the ship every 6 minutes. That's 6 minutes rocket time. Then the ship emits 10 of these 6-minute flashes while going away from the Earth. The 10th flash is going to be emitted 60 minutes after leaving the Earth. Then the ship's clock is going to read 1 o'clock just when this 10th flash is emitted. Now suppose this is the moment that the ship turns around. Our Earth observers don't see the turnaround until they see the 10th flash. Now here it comes. It's going to take some time for it to get to them. Closer, closer, closer. Bam, there it is. 10 flashes, 12 minutes apart. That's 120 minutes, 2 hours. So that means it's 2 o'clock now on Earth. Now the 10 flashes the ship emits when approaching the Earth, they're going to be seen 3 minutes apart, or all 10 in 30 minutes. The first is 3 minutes after 2 o'clock, Earth time. The next is 3 minutes later, and so on, until the last flash is emitted just as the ship whizzes past the Earth. and that's going to be 2:30 Earth time. So a clock aboard the rocket ship reads 2 o'clock, while a clock on the Earth reads 2:30. This checks out. Check the figures. Now let's go through this once again. Watch carefully and compare the clocks. We'll get the same results if we switch frames of reference. The Earth will send flashes now at 6-minute intervals, and the rocket ship will observe them while again departing and returning on what for the ship is a 2-hour journey. 1 hour out and 1 hour back. While going away, the ship's going to see flashes 12 minutes apart. That means it's going to see a total of 5 flashes during this hour of going away. See that? Now while returning, the ship sees flashes 3 minutes apart. It's going to see a total of 20 during the hour of return. For the round trip, then, the Earth emits a total of 25 flashes. At 6-minute intervals, that's 150 minutes, or 2.5 hours. Same results as before. So from either frame of reference, a person on Earth ages more than a person in a high-speed rocket ship. It's not so much a question of who's moving and who isn't, but rather the different space-times experienced. The person on Earth remains in one space-time throughout the experiment, whereas the person in the rocket ship is in a completely different realm of time while traversing space going away from the Earth, and in still another realm of time while traversing space and coming back to the Earth. That's 2 space-times. 2 space-times separated by the acceleration of the ship and turning around. Now that acceleration is interesting in its own right. Get to that in general relativity. But we see that the details of that acceleration aren't really essential in this case. The principal significance of that acceleration is that it marks the changing from one space-time to another. Now, our twins have been in different space-times, and they can meet again at the same place in space, but only at the expense of time. Isn't that great? That's time dilation. Peace.
Where did the time go? Does anybody drop it? Was it a mistake? I've got a notion, circular motion, I'm flying out in the ocean, out in the ocean.